Hi, welcome to a bonus video in the free probability course, and this is about non-crossing partitions and Lukasiewicz paths. Our main goal in this video is going to be counting the size of the following set, the non-crossing partitions of n elements, such that the number of parts, the size of the partition is k. K is some number which is at most n. And we care about what's the size of this set. So just to understand what we're dealing with here, if n equals 4 and k equals 2, I want to count all the non-crossing partitions of 4 elements consisting of 2 parts. So clearly I have the 2 non-crossing pairings of 4 elements, but I also have the non-crossing partitions of 3 and 1. So I have this partition and this partition, and also the 2 funnier looking partitions. So overall, the result is 6, which is smaller than the 4th Catalan number, 14, which we know counts all the non-crossing partitions of 4 elements. Now, what I want to ask is, well, how did we get this number? How did we really count the Catalan numbers not by a recursive relation, but rather direct counting? So we know that the number of non-crossing partitions of n elements equals the nth Catalan number, which we know equals 1 over n plus 1 to n choose n. But originally, we expressed this same number as a different expression, as 2n choose n minus 2n choose n plus 1 or n minus 1. And how did we get to this number? Well, we did not quite count the number of non-crossing partitions of n elements, but rather another set that is counted by the Catalan numbers, which is the non-crossing pairings of 2n elements, which we have shown are in bijection isomorphic to the Dyck paths of 2n steps. Now let's recall what are these. So if we start with a non-crossing pairing of 6 elements, let's say, I want to translate this pairing with the numbers 1 through 6. I want to show how it is translated to a Dyck path. What I do is whenever I look at what we call the northeast-southeast path, such that I go northeast whenever I'm opening a pair. So 1 is opening and 2 is opening as well, but 3 is closing, 4 is opening, 5 is closing, and 6 is closing. And it is pretty clear that this is a bijection because I can translate back from the Dyck path to a partition by a left projection. What do I mean by that? Whenever I have a southeast path, I can project it to the left, by which I get a pair. And I can do this for every such step. And what I get overall, after I do the projection to the left for every southeast step, I get the original partition, the original pairing I began with. If I want to write it a little more formally, what I write is that the Dyck paths of 2n, of length 2n, are all northeast-southeast paths of length 2n, such that I need 2 conditions to hold. Condition number 1 is that the path ends at the point 2n and 0, right? If this is 0 and this is 0 again, I need to end where I started. But also, I want to never go below the x-axis. So I want to never cross this line over here. Now, it turns out, as we know, combinatorially, this is pretty easy to count by direct calculation. I just need to have n of the 2n steps to be northeast, and I'm done. So this translates to the number 2n choose n. The part that's trickier to count is how many paths never go below the x-axis. And the way we counted these was by using a very intelligent trick, non-trivial, to count the number of bad paths. So the way we do that, let's take a bad path as an example. If I start at 0 and I go, let's say, 1 up and then 2 down to southeast. So already at this point, I reached the violation. And then I go twice up and down again. So I ended at 0. I do fulfill the first condition, but I do not fulfill the second one. The way we count the number of bad paths is by projecting from the point of the first violation downwards. And once I do this mirroring path that ends at -2, I can be convinced that this is a bijection from the bad paths to the paths starting at 0 and ending at -2. And these, again, are pretty easy to count, and I count them as the number of bad paths, which are 2n choose n-1 or n+1. And I reached the result I wanted for the Catalan numbers. Now, recall our goal was something else, was to count the number of non-crossing partitions such that the number of parts is k. In order to do so, I want to use this idea of translating from a partition or pairing to a path in order to count and do this bijection in a smart way in order to be able to count these elements. What we're going to do is that we're going to show a bijection similar to one we've shown for the non-crossing pairings and dike paths. We're going to focus on non-crossing partitions and project and show a bijection between them and something that we'll call Lukasiewicz paths. And the definition is going to be pretty intuitive, and I'll explain it shortly by an example. And what we want from this isomorphism for this bijection, we want that if I apply some conditions, such as the number of parts equals k, I can have similar conditions on the right-hand side of the Lukasiewicz paths, such that I'm able to count them, similar to what we did for the dike paths. We'll focus on n equals 7 for the example, and what I'm going to do is draw what is going to be the Lukasiewicz path relevant to the following two partitions on the left. So here, the element 1 is opening a part, and the part it is opening is of size 4. It is 1, 4, 6, and 7. So in this case, similar to the way that if we opened a pairing in the original bijection, we did a step upward. Now we're going to do a step 3 upwards, because the number of parts that are with 1 is 4. So there's 3 additional elements in the part. And 2 is opening as well. So I go one more step up. Then 3 is closing. And 4, well, it's not closing, but it is added to a part that's already existing. And then 5 is in a part of its own. So I do not go down, but I do not go up either. I go straight to the right. And then 6 and 7 are added to parts already existing. And the projection to the left works just as before. So 3 is projected to 2. So I get this part here. And I can repeat the similar process. 5 is clearly on its own. And all the other parts are projected to the, and 4, 5, and 6 are projected to the left to be added to 1. So I get the part I was missing. Okay, let's do another example. So in this case, 1 is opening, but there's only 1 additional element in its part. 2 is opening as well. 3 is closing, 4 is closing. 5 is opening, but it has 2 additional elements. So I need to go 2 up and then go down and down. And these 2 on the right, these 2 paths are called Lukasiewicz paths. So I now need to formalize what do I mean here. So first, I write down what I call an almost rising path, which I denote by AR of n. And these paths are sequences of steps of the form 1a, where a is a natural number, including 0 and -1. Okay, so it can be any positive number, or 0 or -1. And you can see that these are such paths. And when we look at Lukasiewicz paths, are a subset of the almost rising paths with 2 additional conditions. Ending at n and 0, similar to what we did for the Catalan numbers, and also never going below the x-axis. And again, as before, it is enough for us to count the number of Lukasiewicz paths in order to understand the number of non-crossing partitions, but recall that we had the additional conditions here. And the additional condition was that the number of parts is k. And recall that, and not recall, observe that this is something that is preserved under this bijection. So an equivalent question we can ask is the number of Lukasiewicz paths with exactly k non-negative steps. Okay, so it is pretty clear that every time I open a part in the partition, I do a step either a step which is either up or just to the right, but not negative. And so here the number of parts was 1, 2, and 3. So I have the first, second, and fifth step as non-negative. And similar here, I have the first, second, and fifth as well. And now we are left with the not so easy task of counting the number of Lukasiewicz paths. Our goal is to count the number of Lukasiewicz paths of length n that have exactly k non-negative steps. So here we focus in this view here on n equals 7 and k equals 3, as in the examples we've seen for the bijection before. And for counting these, we need to apply an analogous trick to the one we've seen for the Catalan numbers. But this time, I won't use reflection, but rather a rotation. So how does this rotation looks like? First, I add an additional negative steps to the Lukasiewicz paths. So now these are not Lukasiewicz paths anymore, as they go below 0 and end at -1 and not at 0. But they are still an almost rising path. And what I'm going to use is an additional parameter for the rotation. So I can rotate by a number m. So if m equals 3, I start my rotation at 3. And if m equals 4, I will start my rotation at 4. And the way this is going to look like is I'm just copying the path from left to right according to the rotation m. So if I start at 3, I start with a step down and then a step across, and then I have 3 steps down, the third of which is the brown step I added. Then I have the 3 leap up, and then 1 additional step up and 1 additional step down. Clearly, this path ends at -1. And if I rotate by 4, I will start with the step cross, and then I have 3 steps down, the third of which is the added brown step, and then I have the 3 leap up, then 1 step up, and then 2 additional steps down, ending again at -1. And my goal is to show that the Lukasiewicz paths on the left are in bijection to something on the right, using the rotation m as well. And this something is going to be the almost rising paths of length n+1, again with exactly k non-negative steps. Let's be consistent with the colors. With an additional condition that they end at n+1 and -1. Okay, this -1 we see on the right here. And unlike the Lukasiewicz paths that end at n and 0 and have the additional restriction, which makes them harder to count, which is that they never go below the x-axis. These are allowed to go below the x-axis, and it makes them easier to count. And before we move on, I want you to notice that the location of where the lowest point of the path on the right happens is exactly when, exactly after the brown step. Let's look at one additional example to see if this still happens. So here, if I start at 3, I go 1 step down, and then I leap 2 up. And then, it's not pretty, let's do another one. And then I do 3 steps down, the third of which is the brown step. And then I have 2 steps up and 1 step down, again ending at -1. And for m equals 4, I begin with the leap, then I have the 3 steps down, the third of which is brown, and then I have 2 steps up and 2 steps down. This time, notice that I reached the lowest point, the -1 point. I reached it twice, but I want to look at the first location in which I reached the lowest point. And it is pretty clear that this is in bijection with where the brown step was, which makes this translation indeed a bijection between the two. So a bijection between which two sets? The set of Lukasiewicz paths with k non-negative steps times the numbers between 1 and n plus 1, the choice of m, so times, let's say, n plus 1. And this is in bijection with the almost rising paths of length n plus 1 with k non-negative steps, which end at n plus 1 and -1, with no restriction of going below the x-axis. And as before, these are going to be pretty straightforward to count. So let's count them. What we're aiming for is we need to choose the k non-negative steps out of n plus 1 options. So this translates to n plus 1 choose k for choosing what the location of the non-negative steps are. And now the condition that tells us that I need to have k non-negative steps and end the n plus 1 walk at -1 tells me what's the total number of, let's say, upward movements needs to be. So I need to have n minus k upwards, let's say, movements. These can all be in one huge upward step, and all the rest are across, or smaller steps. Depends how you choose it. And this translates into placing this number of balls into the k bins I've mentioned before, and the non-negative steps, and this can easily be shown to translate to n minus 1 choose k minus 1. This is a direct calculation. What this means, and we should not forget this number over here, and we had the Lukasiewicz paths with k non-negative steps in bijection with the thing that we want to count to begin with, which was the number of non-crossing partitions of n elements such that the number of parts is exactly k. And the size of this set is now clearly, I need not forget the number n plus 1 here. It is 1 over n plus 1 times n plus 1 choose k times n minus 1 choose k minus 1, which can be shown in a slightly nicer formula as 1 over n choose k times n choose k minus 1. So let's sanity check. We remember that in the case that n equaled 4 and k equaled 2, we wanted the result to be 6. So if I have 1 over 4, 4 choose 2 times 4 choose 1, I indeed get 6 as I desired. And as we like naming things in combinatorics like the Catalan numbers and the Bell numbers and the Fus-Catalan numbers and other, these are called the Narayana numbers. And this concludes the calculation of the number of non-crossing partitions with exactly k parts.